Right now, as you watch this video, 4 equations written 160 years ago by a Scottish physicist are working magic in your pocket. Your smartphone is receiving radio waves, processing Wi-Fi signals, charging wirelessly, and displaying this video using electromagnetic fields. Every notification ping, every Instagram story, every GPS coordinate, they all depend on Maxwell's equations. But here's the thing. Most engineering students learn these equations as abstract math. They memorize the symbols, pass the exams, and never realize they just learned the operating system of the modern world. Today, we're changing that. We're going to see how 4 elegant equations don't just describe electromagnetic fields, they literally built the digital age. I'm your host at Photon Lab, and this is the story of how James Clerk Maxwell accidentally predicted the future. The Unification Revelation. Picture this. It's 1860. Electricity and magnetism are considered completely separate forces. Scientists think electric fields and magnetic fields are as different as gravity and light. Then Maxwell arrives with a wild idea. What if they're the same thing? But Maxwell didn't just guess. He took the work of 4 brilliant scientists and discovered something extraordinary. Gauss's discovery. Electric charges create electric fields that spread outward. Faraday's insight. Moving magnets generate electricity. Ampere's observation. Electric currents create magnetic fields. Maxwell's addition. Changing electric fields create magnetic fields. But here's where Maxwell's genius shows. He realized something everyone missed. These 4 effects create a feedback loop. A changing electric field creates a magnetic field, which creates a changing electric field, which creates a magnetic field. This creates something that travels through space at 300 million meters per second, the speed of light. Maxwell's jaw dropped. Light wasn't just similar to electromagnetic waves. Light was an electromagnetic wave. And if light was just one frequency, what about other frequencies? Maxwell had just predicted radio waves, microwaves, X-rays, the entire electromagnetic spectrum. He had unified light, electricity, and magnetism into one theory. Equation 1. Gauss's law for electricity. Let's start with a fundamental question. If I place a charge Q in space, what's the electric field at any point? We begin with Coulomb's law. E vector equals 1 over 4 pi epsilon naught times Q over r squared times r hat. Now let's place a real 1 nanocoulomb charge and watch the electric field emerge. I'm creating a coordinate system and placing our positive charge at the center. The electric field radiates outward in all directions. Using E equals 9 times 10 to the 9th times Q over r squared, let's calculate real field strengths. At 1 centimeter, we get 90,000 volts per meter. At 3 centimeters, 10,000 volts per meter. At 5 centimeters, 3,600 volts per meter. Notice how the field decreases with distance squared, but maintains perfect radial symmetry in all directions. Now let's derive Gauss's law by wrapping our charge with imaginary Gaussian surfaces of different sizes. Starting with our first spherical surface, at radius 0.7 meters. The surface area equals 4 pi r squared, which gives us 6.16 square meters. The electric field at this distance equals 18.4 volts per meter. The total flux equals E times A, giving us 113 voltmeters. Now let's try a larger surface at radius 1.1 meters. Surface area increases to 15.2 square meters, but the field strength drops to 7.4 volts per meter. But look at this! The total flux remains exactly the same, 113 voltmeters. Aha! The r squared terms cancel perfectly. This is the key insight. As the surface gets larger, the field gets weaker by exactly the right amount to keep the total flux constant. This reveals perfect spherical symmetry. Same distance from the charge means same field strength, creating uniform flux that's independent of surface size. This leads us to the universal law of electricity. The closed integral of E vector dot dA equals Q enclosed over epsilon naught. This elegant equation works for any charge configuration and any surface shape. It's one of the most powerful tools in electromagnetic theory. And that's how Gauss's law emerges from simple symmetry, the foundation of all electromagnetic engineering. Now let's calculate the electric field in your smartphone's touchscreen capacitor. Given, plate separation D equals 0.1 millimeters equals 10 to the minus 4 meters. Applied voltage V equals 3.3 volts. Dielectric constant epsilon r equals 4 for glass. The electric field is E equals V over D equals 3.3 volts over 10 to the minus 4 meters equals 33,000 volts per meter. That's 33 kilovolts per meter, stronger than the electric field just before lightning strikes. Yet it's safely contained in a device you touch every day. When your finger approaches with epsilon r approximately 80 for human tissue, C equals epsilon naught epsilon r times A over D equals 8.85 times 10 to the minus 12 times 80 times 10 to the minus 6 over 10 to the minus 4 equals 7.1 times 10 to the minus 6 12 farads. The touchscreen detects this 7 picofarad change. Gauss's law for magnetism. Gauss's law for magnetism states that del dot B equals 0. In integral form, the closed integral of B vector dot dA equals 0. This elegant equation tells us that magnetic monopoles don't exist. Let me prove why. Consider any closed surface around a magnet. Every field line that exits the surface must re-enter it somewhere else. Using the divergence theorem, the closed integral of B dot dA equals the integral of del dot B dV. Since the left side equals 0 everywhere, we get del dot B equals 0 throughout space. Let's calculate the magnetic field from a bit on your hard drive. Given a magnetic domain, magnetization M equals 10 to the 6th amperes per meter for typical cobalt alloy. Bit size, 20 nanometers by 20 nanometers by 2 nanometers. Read height, 5 nanometers above surface. Magnetic moment, M equals M times V equals 10 to the 6 times 20 times 10 to the minus 9 cubed equals 8 times 10 to the minus 21 ampere meter squared. Field at read head using the magnetic dipole formula. B equals mu naught over 4 pi times 2m over r cubed equals 4 pi times 10 to the minus 7 over 4 pi times 2 times 8 times 10 to the minus 21 over 5 times 10 to the minus 9 cubed. B equals 1.28 times 10 to the minus 2 Tesla equals 12.8 millitesla. This 12.8 millitesla field change is detected by a giant magnetoresistance sensor, the 2007 Nobel Prize technology that makes high-density data storage possible. Faraday's law. Faraday's law states that del cross E equals minus partial B partial T. In integral form, the closed integral of E dot dl equals minus d phi B over dt. Let's derive this from the motional EMF. Starting with, epsilon equals the integral of V cross B dot dl. Using Stokes' theorem and the relationship between changing flux, epsilon equals minus d over dt of the integral of B dot dA. In differential form, del cross E equals minus partial B partial T. Let's design the transformer in your phone charger. Specifications. Input 120 volts AC, 60 Hz. Output 5 volts DC. Power 15 watts. Core. Ferrite with mu R equals 3000. Primary turns, N1 equals question mark. Secondary turns, N2 equals question mark. Step 1. Turns ratio. N1 over N2 equals V1 over V2 equals 120 over 5 equals 24. Step 2. Core flux calculation. Maximum flux density for ferrite. Bmax equals 0.3 Tesla. Core area. A equals 1 square centimeter equals 10 to the minus 4 square meters. Phi max equals Bmax times A equals 0.3 times 10 to the minus 4 equals 3 times 10 to the minus 5 Webers. Step 3. Primary turns using Faraday's law. V1 equals N1 times d phi over dt equals N1 times omega times phi max. For sinusoidal AC, 120 equals N1 times 2 pi times 60 times 3 times 10 to the minus 5. N1 equals 120 over 2 pi times 60 times 3 times 10 to the minus 5 equals 1061 turns. N2 equals N1 over 24 equals 44 turns. So your tiny phone charger has over 1000 turns in the primary coil, all perfectly calculated using Faraday's law to safely convert wall power to charge your battery. Ampere-Maxwell law. The original Ampere's law was del cross B equals mu naught J, but Maxwell realized this was incomplete. Watch what happens when we check current conservation. Del dot del cross B equals del dot mu naught J equals mu naught del dot J. Since the divergence of any curl is always 0, del dot J equals 0. But we know from charge conservation, del dot J plus partial rho partial T equals 0. This only works if partial rho partial T equals 0, no changing charge. Maxwell fixed this. Del cross B equals mu naught J plus mu naught epsilon naught partial E partial T. The displacement current, mu naught epsilon naught partial E partial T, makes everything consistent. Now watch the magic. Take the curl of Faraday's law. Del cross E equals del cross minus partial B partial T equals minus partial over partial T del cross B. Substitute Ampere-Maxwell law in free space where J equals 0. Del cross E equals minus mu naught epsilon naught partial squared E partial T squared. Using the vector identity del cross E equals del dot E minus del squared E, and noting that del dot E equals 0 in free space, del squared E equals mu naught epsilon naught partial squared E partial T squared. This is the wave equation. The wave speed is c equals 1 over square root of mu naught epsilon naught equals 299,792,458 meters per second. Let's calculate the radiation from your phone's antenna. Given frequency f equals 2.4 gigahertz for Wi-Fi, antenna length L equals lambda over 4 equals 31.25 millimeters. Current amplitude I naught equals 10 milliamperes. Distance r equals 1 meter. Far field electric field from dipole antenna. E theta equals J times eta naught I naught L over 4 pi r times e to the minus j k r times sine theta, where eta naught equals square root of mu naught over epsilon naught equals 377 ohms, the free space impedance. E theta equals J times 377 times 10 to the minus 2 times 31.25 times 10 to the minus 3 over 4 pi times 1 times e to the minus j k r times sine theta. E theta equals 0.0374 times e to the minus j k r times sine theta volts per meter. Power radiated, P rad, equals eta naught I naught squared over 6 pi times KL over 2 squared equals 377 times 10 to the minus 2 squared over 6 pi times pi over 2 squared equals 6.2 milliwatts. Your phone radiates 6.2 milliwatts in a precise pattern calculated using Maxwell's equations, enough to reach the Wi-Fi router across your house. Engineering problem 1, 5G antenna array design. Design a 5G beamforming array to focus signal energy toward a specific user. Given frequency f equals 28 gigahertz for 5G millimeter wave. Array 8 by 8 elements, spacing d equals lambda over 2. Target 30 degrees off bore site. Required gain 20 dBi. Step 1. Calculate wavelength and spacing. Lambda equals c over f equals 3 times 10 to the 8th over 28 times 10 to the 9th equals 10.7 millimeters. D equals lambda over 2 equals 5.35 millimeters. Step 2. Phase progression for beam steering. To steer beam to angle theta equals 30 degrees, beta equals kd sine theta equals 2 pi over lambda times lambda over 2 times sine 30 degrees equals pi over 2 radians. Step 3. Array factor calculation. AF equals the sum from n equals 0 to 7, sum from m equals 0 to 7, of e to the j times n beta x plus m beta y, for 30 degree steering. Beta x equals beta y equals pi over 4. Step 4. Calculate achieved gain. For 64 element array with uniform illumination, G equals efficiency times n equals 0.8 times 64 equals 51.2 equals 17.1 dBi. Need 3 dB more gain? Add amplitude tapering or increase array size. Engineering problem 2. Wireless power transfer efficiency. Calculate the efficiency of wireless charging for an electric bus. System specifications. Power requirement, 100 kilowatts. Air gap, 20 centimeters. Frequency, 85 kilohertz. Coil diameter, 80 centimeters. Quality factors, Q1 equals Q2 equals 100. Step 1. Calculate mutual inductance. For two circular coils, M equals mu naught, square root of A1, A2, over 2 times the quantity 2 minus k squared times k of k minus 2 times e of k, where k squared equals 4 R1, R2, over the quantity R1 plus R2 squared plus h squared. With R1 equals R2 equals 0.4 meters, h equals 0.2 meters, k squared equals 4 times 0.4 times 0.4 over 0.8 squared plus 0.2 squared equals 0.64 over 0.68 equals 0.94. M equals 245 microhenries. Step 2. Coupling coefficient. Self-inductance L1 equals L2 equals 500 microhenries, calculated for coil geometry. K equals M over square root of L1 L2 equals 245 over 500 equals 0.49. Step 3. Maximum efficiency calculation. Efficiency max equals kq squared over the quantity 1 plus square root of 1 plus kq squared squared. With kq equals 0.49 times 100 equals 49, efficiency max equals 49 squared over the quantity 1 plus square root of 1 plus 49 squared squared equals 2,401 over the quantity 1 plus 49.01 squared equals 95.8%. 95.8% efficiency. The 4.2% loss means 4.2 kilowatts of heat generation, requiring active cooling. Engineering Problem 3. Electromagnetic Interference Analysis. Analyze EMI from a switching power supply in a smartphone. Given, switching frequency 1 MHz, rise time 1 nanosecond, peak current 2 amperes, loop area 1 square centimeter. Step 1. Fourier analysis of switching waveform. For trapezoidal current with rise time tr, I of f equals I naught times sine pi ftr over pi ftr. Step 2. Radiated power calculation. Magnetic dipole moment. M equals I times A equals 2 times 10 to the minus 4 equals 2 times 10 to the minus 4 ampere meter squared. Radiated power at frequency f. P of f equals eta naught k to the fourth m squared over 6 pi equals 377 times 2 pi f over c to the fourth times 2 times 10 to the minus 4 squared over 6 pi. At 100 MHz, the 100th harmonic, P of 100 MHz equals 45 microwatts. Step 3. Field strength at 3 meters, the FCC test distance. E equals square root of 377 times P over 4 pi r squared equals square root of 377 times 45 times 10 to the minus 6 over 4 pi times 9 equals 0.69 volts per meter. Convert to dB microvolts per meter. 20 times log of 0.69 times 10 to the 6th equals 116.8 dB microvolts per meter. This exceeds FCC Class B limit of 100 dB microvolts per meter, needs EMI filtering. Maxwell died in 1879, never seeing radio, television, computers, or smartphones, but his equations predicted them all. Today's engineering students will build technologies Maxwell never imagined: room temperature superconductors, quantum computers, fusion reactors, brain-computer interfaces. But they'll all rely on the same 4 equations a Scottish physicist wrote by candlelight 160 years ago. These aren't just equations, they're the source code of the electromagnetic universe. And now that you understand them, you're ready to write the next chapter. This is Photon Lab, where we make physics feel like engineering magic. Subscribe for more engineering adventures, and remember, the future is electromagnetic.